In this video, we're going to discuss CRA models for whole number multiplication strategies that are based on place value and properties. So this is not an exhaustive list, but just some common strategies that students might use that don't use formal algorithms, but are using different concepts related to place value and properties. So this first one is going to be repeated addition. So for this example, we're looking at 4 times 7. And repeated addition is a strategy to solve multiplication problems by using addition. So here we have 4 groups of 7. So how a student might solve this using repeated addition would just be add on, right? They're just doing addition over and over and over. That's why it's called repeated addition. So we're starting with 7, and we add on another 7 to get 14. Then on 14 we add on another 7 to get 21. And then on to 21 we add 7 more to get to 28. Okay, so this would be one example of a concrete model. Usually, like area models and arrays are going to be pretty common with this strategy for repeated addition. A representational model would look pretty similar. I'll just draw an array since it'll be a little bit faster. Again, so we have 4 groups of 7, but we're not necessarily thinking this is 4 times 7. We're thinking this is 7 plus 7 plus 7 plus 7, but soon we'll still move through that in the same process. And then how we're thinking of this, kind of what this abstract model would be to align with the concrete and the representational model is, rather than thinking of this as 4 times 7, right, recognizing 4 groups of 7 means that I have a group of 7 plus another group of 7 plus another group of 7 plus another group of 7. Okay. And then some students might add on to this to get to 28. Others might kind of pair these two to get 14 plus 14. You get to 28. So it would look like if we paired these two up. So might be some different strategies, but that's the first one. Kind of based on place value and properties as repeated addition. Our next one that we'll look at is going to be called compensation. Okay, so for this one, we're going to look at 4 times 19. So in this compensation strategy, we're basically going to modify this problem just a little bit to make it easier to solve. And then we're going to have to make some adjustments. So this is kind of one example of how you might use this compensation strategy. So here at 4 times 19, we might not know that off the top of our head, but we might recognize, well, 19 is really close to 20, and I know what 4 times 20 is. So what we're doing, and I don't have a separate color with me right now, but if we have a separate color, that'd be good to add in right here. So I'm going to just set mine kind of off to the side since I don't have a separate color, but kind of how we're thinking of this is I can just visualize this 4 times 19, it's 4 groups of 19 as 4 groups of 20. So each group has 20. So I know I have a total of 80. Right? I can think of 8 10s or 4 20s, however we would need to go about that. But then what I need to do at the end here, right? I don't actually have 4 groups of 20. I just have 4 groups of 19. So I had 1, 2, 3, 4 too many ones that I counted in here. So then I need to subtract 4 from this group of 80. All right, so I'd subtract those 4 to see that I had 76. And then I'm not going to do the drawing for this one just because it's going to be the exact same as the concrete model, but a common representational model would be doing those drawings. I'll just give a quick, right, instead of drawing all the hash marks, right, that might be a 10. And those might be your ones. And then for your extra, right, you might do like a little X or something, right, just to show that you have, just to kind of keep that extra one designated as opposed to just adding that normal looking one in there, because you might get that mixed up. Okay. And then the abstract model that aligns with this, right, essentially we're just rewriting this quantity of 19 as 20 minus 1. Right, or you can think of 20 plus -1. Right? So then here, right, we're just applying that distributive property, right, the 4 times 20, and then since we have a minus in there, right, minus 4 times 1. So that's the distributive property. So then we get, right, that 4 groups of 20 was 80, but that we had to add 4 pieces back in. So we need to subtract those back out, right? That's a compensation at the end to get this to 76. All right, and then our next one that we're going to look at is going to look kind of similar to the compensation strategy, but it's going to be a little more. We're not going to modify the original number. We are going to use some place value concepts and that distributive property too. So this next one is thinking of this in terms of expanded form. Get these aligned back up here. Okay, so rather than doing a compensation rate, it's the exact same problem, 4 times 19. Instead of doing some kind of compensation strategy, we might think of this as well. I know I have 4 tens, so we're kind of thinking of these tens separately. So I have 4 tens, so I have 40 right there. And then here I have 4 groups of 9, 4 times 9, right? So if that's a fact that we know 4 times 9, we can see that that's 36. If we don't, we can, apply some other properties, break that up more, do 3 times 4 times 3 or something like that. But here, so then we have 40 plus 36, so then we still get to that 76. Okay. And then as far as your representational model will look pretty similar, so I'm not going to draw that one again just to kind of save on time. But again, it would be, you'd start with your tens and ones, so you'd have 4 of these groups, and you might just draw some arrows or draw an entire second line, all the tens together, all the ones together, and then show that, if you want, you can show that regrouping, and then that combining with addition. And then the abstract model that would go along with this to kind of show the actual steps that we're doing here. Right, we're starting with 4 times 19. And again, we're breaking this apart by place value. So we're kind of similar to that compensation strategy. We're doing some kind of modification to that multiplier. So what we've changed this into, kind of decompose that 19 into 10 plus 9, and then again apply that distributive property. So we get 4 times 10 plus 4 times 9. For the 4 times 10, right, that's the 4 tens. We had 40. And then 4 groups of 9, 36. And then again, we want that total. We're going to think of that as one total quantity, so we're adding those together to get 76. Right, so that's our expanded form, and then we have 2 more that are going to be related. We'll start with the area model here. Okay, so I'll move this around a little bit, and we're going to kind of relate this to another strategy kind of at the end, just once you get to the abstract portion here. Okay. But so with our area model, what we're looking at is 12 times 34. So again, that's going to be, we're kind of conceptualizing the groups as the rows. So we have 12 rows that each have 34 cubes in them. Okay. I'm going to break these apart just a little bit more so you can kind of see, right? So these are the big hundreds units for the base 10. So 10 by 10, so those have a length of 30. And these are going to be tens. These These are going to be 1s here. Okay, so we have this length of 34. Right, so each row is the size of 34, and there's going to be 12 rows, right? So 10 and then 2. Okay. So we're using an area model to model these multiplication problems. What we're essentially doing is kind of that, some different form of that expanded form type of strategy. So what we have modeled here on the in this kind of top left portion, I separated them so we could kind of see these 4 different quadrants a little bit more easily. So this portion, this area, right, this is literally 3 hundreds. Right, we have 3 of these hundreds units. And this is an area of 10 rows that have a size of 30, so 10 times 30. So you can see in our 12 times 34, we're just multiplying the 10s together. Down the bottom left here, right, we have 2 rows of 30, right, these are all 10s. So 2 rows of 30. So again, you can see we're multiplying the 1s digit from one of our multipliers by the 10s digit of our other multipliers. We have 10s here. Kind of similarly here, we have 4 rows that, or sorry, 10 rows that each have a size of 4. Right, so there's the 10s place from that 12 multiplied by the 1s place in that 34. And then over down here in the bottom right hand corner, right, we have 2 rows of 4, and that's the 2 times the 4 there. Okay, so it's similar, pretty similar to that expanded form strategy, but just more arranged in an actual area model. Okay, so here we can see we have 3 hundreds. Down here I have 6 10s. Over here I have 4 10s. Right, so I have 6 10s and 4 10s, so that's another 100. So I have a total of 4 hundreds, and then over there I have 8 1s. So this is 12 times 34 would give me 408. Okay. Our representational model, I'm going to show, I'm not going to draw all the tick marks, but I'll still show just kind of our 4 quadrants a little bit. This might not necessarily be drawn quite to scale. So label is 30 and 4, and then 10 and 2. Right, so this total length here is 12. And this total width here is 34. So again, this 30 times 10, right, there'd be 300s in there, just like there was in the concrete model. Over here, there'd be, right, we have 10 rows of 4, right, we'd have 40 or 4 10s, just like was on the concrete model. Here again, we have 2 rows of 30, so there's a total of 60 or 6 10s. And you can see we have 2 and 2 and 2. And then the bottom right hand corner, right, we'll just have 8. Okay. So this is kind of a not necessarily drawn quite to scale area model, but this is a common representational model to go along with this. So just so we don't have to pull the base 10 blocks out all the time and have all the little tick marks drawn in there. Okay. And then for the abstract model, again, what we're showing here, I'm going to show kind of two different strategies that kind of line to this, and one's actually pretty similar to the drawing, to the representational model. Okay. So when we had 12 times 34 again, since we thought of this as the 10s times the 10s, 10s times 1s, 10s times 1s, and then 1s times 1s. Okay, so what we essentially did was we decomposed, first what we did was decomposed each of these multipliers by place value. And so, not times. So we had 10 plus 2 times 30 plus 4. Okay. So if we're going to apply the distributive property, right, this 10 times 2 I'll just draw this down here. So I'll go kind of the long way just to stick to the kind of what we saw the original distributive property like. So this entire quantity of 10 times 2, we want to distribute throughout this 30 plus 4. Okay, so you can think of this as the 10 being distributed to the 30 and to the 4, and then the 2 will eventually be distributed to the 30 and the 4. Okay. I'll put some brackets in here. All right, so we're just starting with that entire quantities being distributed to each of those, right? So that entire quantity of 10 times 2 is being distributed to the 30 and to the 4. And then we're going to do the distributive property again for each of those subsets in those brackets. So then this, right, 10 times 30 and then plus 2 times 30 and then 10 times 4 and then 2 times 4. Just run out of room there. All right, but this 10 times 30, right, that's the, right, this is our area, that's 10 times 30. 2 times 30, right, 2 rows of 30, so that's this quadrant down here. 10 times 4, 10 rows of 4, and then 2 rows of 4 is this portion down here. Okay. So then again, what we found was that 10 times 30, we had 3 hundreds, 2 times 30 plus 6 tens, or 60, 10 times 4, 40 or 4 tens, and then the 2 times 4 we had 8. So again, we had 300 plus 60 plus 40 plus 8 is equal to 408. So another way to think of this, I just want to kind of show, right? So we already kind of looked at this with the representational model. But this is terminology that's used a little bit more frequently. It's called the box method. So the box method is a representational model for applying that distributive property. So this is kind of a, this is a replacement for, when I say replacement, it does the exact same thing, but a different strategy for using that FOIL strategy, right? So we do stands for first, oops, first, outer, inner, and then last. Okay, so this is saying when we have, I'll write this over, let's go here. Right, this FOIL strategy, right? The first is saying we multiply the first values in our two different grouping symbols here, right? When they're multiplied together, so the 10 times 30. Outer is just the furthest left and the furthest right, right? The 10 times 4. Inner are going to be these two that are on the inside, the innermost, and then the last are going to be the two last terms in each of the quantities. Okay. So this is going to be, this aligns exactly kind of with the abstract one that we just showed, right? Because we did eventually get the 10 times 30, which is the first. We got the 2 times 30, which is the inner. We got the 10 times 4, which is the outer, and then the 2 times 4, which is the last. So we did it in just a little bit different order. What I want to show is this box method and how that relates to both the area model and that FOIL model that some might be more familiar with. Okay, so for this box method, this is similar to that representational model that I showed. So this is just a not drawn to scale area model. And so we still have that height of 12, we have that width of 34, and we're just finding these kind of partial products, which is an algorithm that we'll talk about later. But here we're just looking at what we're visualizing in this square is 10 rows of 30, and we're trying to think of what is the size of that. So 30 times 10, or 10 times 30 would be 300. 10 rows of 4, 10 times 4 is going to be 40. 2 rows of 30 is going to be 60, or 6 tens. And then this 2 times 4, 2 rows of 4 is going to be 8. Okay, so then using that box method again, all that we're doing, this is just a representational model of this concrete area model. Right, all those quantities align perfectly with what we found right there. Right, we have 300s. Right, we have 4 tens right there. 6 tens in the bottom left. And then 8 ones right there. Okay. And again, with that FOIL method, right, let's set this one down. Right, the 300, that's the first, right, 10 times 30. This 10 times 4, 10 times 4, right, that's the outer. It's 2 times 30, the 60 there. That's the inner, 2 times 30 there. And then this 2 times 4, the 8, that's the last, right, the last in each of the grouping symbols in the parentheses. So this box method contains all the exact same components as that first, outer, inner, last. This is used a little more frequently in current math education, just because it is more easily related to that area model. Okay. So again, not a fully exhaustive list of different strategies based on place value and properties, but these are just some of the common ones that are used for multiplication. You can see that especially as you grow in size of your multipliers, as those increase in quantity, then these base 10 blocks are going to be pretty common concrete models, and then drawings to align with those. And then abstract really is going to be more of those equations and kind of growing in complexity using a lot of the grouping symbols and applying some of those properties.